Hi, I'm Ryan, and I'm teaching y'all about function behaviors. So let's say if we have the graph of y is equal to x plus 3 squared times x plus 1 times x minus 2. Now, notice how, kind of all these roots, right? So we have x plus 3 squared, meaning that one of the roots of the polynomial is negative 3. If we have x plus 1 squared, well, the root that corresponds to that is going to be negative 1. And if I have x plus 2, the root that corresponds to this is going to be 2, right? So I'm just pointing out all the roots of this polynomial, or all the places where this function touches the x-axis. Now, in this video, I'm going to be talking to y'all about kind of the behavior around this root. And what do I mean by that? Well, there's a little interesting pattern going on. So when I have, in this case, x plus 3 to the second power, well, what I notice is that this function does not cross the x-axis when it touches this root, right? Because you can think about this, right? So this right over here, all of this section I'm highlighting is the positive kind of y-axis, right? This is when all the y values are positive. And right down here, this is when all the y values are negative. Now, what you notice is that at x is equal to negative 3, well, this function kind of stays in one side, right? It stays at one side. And this happens when the exponent is even. While if we have the root that corresponds to x plus 1, aka negative 1, what you notice is that this function switches from one side to another. And when you have x minus 2, the root that corresponds to that is x is equal to 2. And you notice here how this function, once again, switches from one side to the other side. So yeah, that's kind of like the behavior of functions, polynomials. So when you have an even exponent on this factored form for the polynomial, well, what's going to happen is that you're going to kind of stay in one section, right? You're going to stay in either kind of the positive y section or the negative y section. You're not going to cross this x-axis when the exponent is even. However, if the exponent is odd, then you're going to cross from one section, in this case the positive section, to the other section, the negative section. Or another way you can think about it is you're going to cross this x-axis. So that's kind of how you determine kind of some function behaviors. Let's say if I have this function, y is equal to x minus 5 times x plus 3 squared times x minus 2. Well, if you take a look here, right, when this right over here touches, that's negative 3, right, we know that this right over here, x plus 3 squared, corresponds to this root, right? Because when you plug in negative 3 here, well, this is going to make this thing 0, so the whole thing zeroes out. So this factored part of this polynomial corresponds to this root. And you notice how when the exponent of this factored polynomial is even, well, that makes it so that it kind of stays on one side. It does not cross the x-axis. While when you have something like x minus 2 to the second power, this corresponds to this root at x is equal to 2. And at x is equal to 2, well, it crosses from the x-axis, right? It crosses the x-axis from one, in this case, the positive section to the negative section. All right. Once again, you look at x minus 5 to the first power, and you notice here how, well, once again, it crosses from one section to the other section, or crosses the x-axis, because the exponent of this part is odd. Now, my goal for y'all at the end of the video is to learn how to sketch polynomial functions. So if I give you this equation right over here, well, how is it going to look on a graph? So maybe sketch the shape of it, right? So that's kind of the goal by the end of the video. Now, there's a couple of function kind of patterns you need to memorize. So when you have y is equal to x to the second power, I'm sure you all know what this looks like, right? This is a parabola shape. As your x value approaches infinity, well, your y value also approaches infinity. Basically, if the x value gets bigger and bigger and bigger, the y value is also going to get bigger and bigger and bigger, right? Up to infinity. It's going to approach infinity, right? And same can be said on the other side, right? If I choose, let's say, a negative x value, right, as x approaches negative infinity, right, as you go down to the left, well, the y values are just going to get bigger and bigger, right? The y values are just going to get bigger and bigger. So that's kind of two key features of kind of this graph, right? As x approaches infinity, the y value is also going to approach infinity, right? It's just going to keep growing. And same can be said when as x approaches negative infinity, the y value is also going to approach infinity. Now notice how when I enter in even exponents, okay? So if I enter in the even exponent, right, it looks the same, right? It still has this U shape. It's just a little kind of steeper. But, you know, the pattern is still there, right? As x approaches infinity, y value is also going to approach infinity. And as x value approaches negative infinity, the y value is also going to approach infinity. Now, when your exponent is odd, let's say if you have y is equal to x to the third power. Well, what's going to happen is as x approaches negative infinity, basically as the x value gets more and more negative, the y value also gets more and more negative, right? It's going to approach negative infinity. Meanwhile, as the x value approaches infinity, well, the y value is also going to approach infinity, right? As x value gets bigger, y value is always going to get bigger. And this is the case for, let's say, y is equal to x to the first power, right? Y is equal to x to the fifth power, x to the seventh power, 9th, 11th, okay? So just kind of a quick recap of what we learned. When exponent is even, well, it's going to look like a U shape. It's going to be a parabola shape. When the exponent is odd, it's going to have this sort of, it's like a weird S shape, sort of. So yeah, that's kind of the features of a parabola that you got to know. So these are just some important things you got to memorize. And don't forget that if you put a negative sign in front of the thing, it flips it. So in this case, just do that again, right? If you put a negative sign in front of y is equal to x to the second power, it's going to flip around. It's going to be reflected across the x-axis. And if, let's say if I have this thing right over here, put a negative sign, it kind of flips, right? Flips across the x-axis. Now, one thing you might be wondering is, okay, if I have something like y is equal to x to the second power, I know what that looks like. But what if I have something like y is equal to x to the third power plus x to the second power plus 3x plus 1? How do I know what this looks like? Now, the way to answer this problem is, well, all you have to do, it's actually way simpler than you think. All you have to do is just look at the biggest term. In this case, right, the biggest term in this case is this x to the third power, right? The term with the highest exponent, okay? So you're going to look at the term with the highest exponent, and that's the way it's going to look like. So if I have y is equal to x to the third power plus x to the second power plus 3x plus 1, I know it's going to look something like this x to the third power, right? So that's kind of how you determine the behavior, or kind of how like a function looks like, without even having to graph it. All you have to do is just look at the biggest term, and using what we've learned about functions, right? We know even functions look like this, odd functions look like this, right? Using what we learned about this, well, we can solve this, right? We can predict how functions look like. And in this case, y is equal to x to the third power plus x to the second plus 3x plus 1. And once again, right, it still has this similar shape. If I give you something like, let's say, I'm just going to label this real quick. So if I give you something like y is equal to x to the fourth power plus 3x to the third power plus x plus 3, how is this function going to look like? Well, kind of all you have to do is just focus on the biggest term, the term with the highest exponent. We know that because x to the fourth power is even, we know that things with kind of the even exponent, they have this parabola shape, which means that this function right over here is going to look something like this. It's not exact, but, you know, if you graph this out, you know, it kind of looks like that, right? It kind of has this U-shaped feature. There's a little bend here, but you kind of get the same shape, right? As x approaches infinity, the y value also approaches infinity, right? So kind of the concepts right over here are still the same. All right, we can do one more example. So if I have, let's say, y is equal to x to the seventh power plus x to the sixth power plus 3x to the fourth power plus 3, all you have to do to determine how this function looks like is you can kind of just look at the term that's like the biggest, in this case, x to the seventh power. And we know that odd exponents look something like this, which means that this function is going to look somewhat like this. It's going to have somewhat of this behavior. And if I graph this out, right, as this similar behavior. Now we're going to be shifting gears a little bit. So we kind of learned how to predict how functions look like in this form, right, in a non-factored form. But what if I have a function like this, where it's in the factored form? How do I predict how this function looks like? And the thing about functions being in factored form is you can actually get a really good kind of sketch of how the function looks like a really good sketch. Because remember what we learned in the beginning, right? How when the function's exponent is even, well, it's not going to cross the x-axis. When the function's behavior, in this case, is odd, right? When the function's thing is odd, well, it's going to cross this x-axis. So when the function is in its factored form, you can actually get a really good sort of sketch of how the function looks like. So the first step to finding out how this function looks, I said that word like 100 times, but you're going to get all the zeros. So what are kind of the x-intercepts of this graph? When does this function become 0? Well, when x is equal to -6, well, then if you plug in -6 here, this is going to be -6 plus 6 is 0, and 0 times whatever this is just 0, right? So -6 is one of our zeros. And also x is equal to 1, right? When you plug in 1 here, 1 minus 1 is just 0. So 1 is also another 0 in this graph. The next step of what you want to do is you want to count out how many x's are here. So in this case, I have x plus 6 to the second power. So if I have x plus 6 to the second power, right? X plus 6 to the second power can be rewritten as this, right? X plus 6 times x plus 6, and you still have this x minus 1. And we want to count out how many zeros there are. So how many x's there are. So we have 1, 2, and 3 x's. Meaning that if we multiply all of these together, the highest term we're going to get is x to the third power, right? You can all agree that if we multiplied everything out together, we're going to get x to the third power and so on, right? We're only focusing on the highest term that we're going to get. We don't care about the other terms, okay? So that's the second step. The second step is determining how many x's there are to get kind of the highest power. Now we know that the function y is equal to x to the third power. We know that looks something like this. So kind of we can sketch the beginning of that. Right? We know that it's going to hit this root. Now the thing is, in our function we have an even exponent corresponding to this root. And remember how we said when the exponent of the root, in this case that corresponds to the root, is even, well, it's going to stay in the same kind of y area. So it's not going to cross this x-axis. It's going to stay below it in this case. Now eventually this function has to once again go back up, right? Because it has to hit this root at x is equal to 1. It has to hit this root. Now because this is x to the first power, right? This term has an odd exponent. Well, what we're going to do is it's going to cross the x-axis. And that's how the function kind of looks like. This is just the sketch of the function. And if we enter it in, we enter this in, right? This is a pretty damn good sketch of what the function looks like. Now, this can get really confusing because it's combining a lot of concepts together. It's combining how kind of the functions of even exponents and odd exponents look like. And it's combining the concepts of even kind of, I guess you can say, roots or like odd roots, right? Odd behaviors around roots. So it's kind of two concepts in one. So, and it can get pretty tricky. So I'm going to do more practice problems. So if I have, let's say, y is equal to x minus 5 to the third power times x plus 1. What is this going to look like? Your first step is determining the roots of this function. So what x values do I have to put in to make my y value equal to 0? If I plug in x is equal to 5, well, I get 5 minus 5, which is 0. 0 times this is 0. So that means 5 is one of the roots, and -1 is one of my roots, right? If you plug in -1 here, -1 plus 1 is just 0. 0 times whatever this is 0. So our y value is also going to be 0 at this point. Now we're gonna kind of find out how many x's there are. So in this case, I have x minus 5, and we're doing this 3 times, right? So it's x minus 5, x minus 5, x minus 5 times x plus 1. So there are 4 x's, meaning that when we multiply all of these together, the term with the highest power is x to the 4th power, right? We're going to get x to the 4th power if we multiply all of these x's together. And we know that whenever we have an even exponent, it's going to look like a parabola, which means that we have to start up here. The reason why we do this step is because let's say we had 3 x's, right? We know that the function x to the 3rd power looks something like this. So we would have to start down here. However, because we had 4 x's, well, we know that 4 x's leads to this parabola shape, meaning that we have to start up here. And that's exactly what we're going to do. We're going to start up here, and it's eventually going to reach the root. Now at x is equal to -1, the root that corresponds to this is this root right over here, right? This root corresponds to x is equal to -1. And notice how it has an odd exponent, meaning that it's going to cross the x-axis, right? Whenever the exponent is odd, it crosses the x-axis. Now it's eventually going to go back up to hit the second root, right? It has to hit the second root somehow, so it has to go back up. Now, because the second root has an odd exponent, it's going to cross the x-axis. So it's going to look something like this. This isn't the best graph, but it should be this U shape. And by this, y is equal to x minus 5 to the 3rd power times x plus 1, right? Notice how, once again, it has this U shape. It has this curve. It has a little bit of a curve there, but the thing is, it's a pretty damn well sketched, right? The root is -1, 0, 5, 0. It crosses here, and then it crosses here, right? And, all the features are there. So, yep, we're going to do another example. Let's say y is equal to x minus 5 to the 3rd power times x plus 4 to the 2nd power times x minus 5, x minus 3. A little challenge problem. And this is to the 1st power. So we're going to label our roots. That's our first step, right? So we have a root at, and in this case, x is equal to 5. I'll place it around here. We have a root at x is equal to 5, a root at x is equal to 3, and we have a root at x is equal to -4. Now, once again, we're going to find out how many x's there are. So there are 3 x's from this term, right? If we expand this as x minus 5 times x minus 5 times x minus 5, so there are 3 x's from this term. There are 2 x's from this term, right? Because we saw it's x plus 4 times x plus 4. If we expand this, and this term right over here, there's only 1 x, which means that if there's 3 x's here, 2 x's here, 1 x here, well, if we multiply all of them together, we're going to get x to the 6th power, right? If I have x minus 5 3 times, so 3 x's here, x plus 4 2 times, 2 x's here, and x minus 3 1 x here. If I multiply all of them together, I'm just going to get x to the 6th power. So kind of a quick and easy trick you can do to find the biggest power is you can just add up all the exponents in this thing, right? 3 plus 2 plus 1 gives us 6, which is going to be the highest kind of power. And we know that y is equal to x to the 6th. This function looks something like this. It looks like a parabola, right? We know that because the exponent is even. Even exponents have this U shape. So that means that we are going to start all the way up here. It's going to touch this root. Now the thing is, right, at x is equal to -4, we know that this right over here, let me just switch to another color. So if we have this root right over here in its factored form, x plus 4 to the 2nd power, we know that when the exponent is to the 2nd power, or when our exponent is even, then we stay at kind of the area that we were originally in. We do not cross the x-axis when the exponent is even, which means that this function is going to curve back up. This function is going to curve back up. All right, so we found out kind of how many x's there are to find out our initial starting point, but then after that, we use kind of the behavior of functions around the root to kind of help us sketch the rest of it. So in this case, right, because our exponent is even, we're going to kind of hit the x-axis, and then we're not going to dip below it. We're going to stay where we are. We are not going to cross the x-axis. Now, we eventually have to go back to this root somehow, right? We eventually have to hit this root. So we're going to go back down, right? We have to hit the root somehow. So it's eventually going to go back down, and it's going to hit this root right over here, this part of our polynomial, x minus 3 to the first power, which has a root of 3. So once again, I'm just going to type this up here, but when our exponents are even, well, it does not cross our x-axis. But when our exponent is odd, then it does cross our x-axis. And now, once again, we have to hit this root somehow. So once again, our thing is going to come back up, right? It's going to dip down, and because there's a 0 right over here, it has to come back up to hit it, right? And we have x minus 5 to the third power right over here. That corresponds to this root. And we know that since we have an odd exponent, well, it's going to cross the x-axis. So our final function is going to look something like this weird W shape. And notice how it kind of still has the same features as y is equal to x to the 6th power. Right? You notice how as x approaches infinity, y value also approaches infinity. And as x approaches negative infinity, y value also approaches negative infinity. So kind of keep that in mind as well. And let me sketch this. Right, once again, it has this W shape, right? It goes down, and then it goes back up, and then it goes down again, crosses the x-axis, and then finally crosses the x-axis again. That's exactly what we have here, right? It goes down, then it stays up top, then it goes down again, and then goes back up again, right? Exactly what we have here. So this is just a pretty cool way to kind of graph functions. And don't forget that if we had this negative sign in front, our graph would look entirely different. We would have to kind of flip everything around. It would look. If we had a negative sign on the front, our function would look like this. Right? It would just be flipped around. All right. So because our sign in front of our function is positive, it's going to look like this top graph right over here. But just be wary that if our function had a negative sign in the front, well, everything would have to be flipped around.